Hi there, welcome to my channel. In this video, I'm going to discuss about the implementation of LRU cache. Let's look at the problem description. We need to design a data structure that follows the constraints of least recently used cache. We have to implement the LRU cache class with a constructor function that initializes the cache with the given capacity, and get method and put method. So the get method key return the value of the key if it exists, otherwise we have to return -1. For the put method, if the keys already exist in the cache, we have to update the new value, otherwise we have to add a new entry for this key value. If there is no space in the cache, then we have to evict the least recently used item and then add this new item. The functions get and put must each run in order of 1 average time complexity. So let's take a look at the example 1. So we are given the list of operations and the corresponding input values, and first we call the LRU cache operation with capacity 2, and then we call put with 1,1 as the key value pair, and then second put operation 2,2 as the key value pair. So the cache will have two elements that reached its capacity 2, and then we make a call to 1. So we are accessing 1, so this will become recently used, and then when we make a call to put 3,3, least recently used item 2 is removed from the cache and 3 will be added to the cache. Next, when we do call the get operation with 2 is not there in the cache, so we get -1. Next we add 4,4, okay, because 1 is the least recently used, 1 removed from the cache and 4 will be added. So now 3 and 4 are in the cache. So when we make a call to get, when we do get operation on the key value 1, there is no element in the cache, so we get -1. Then we do get operation on the key 3, so we get value 3, and then we do the get operation on value 4, we get 4. The constraints for this problem are the capacity value is ranging from 1 to 3,000, and the key value is ranging from 0 to 10,000. The value will be ranging from 0 to 100,000. At most 200,000 calls will be made to the get and put operation. Let's look at the approach to solve this problem. We are given this list of operation and the corresponding input and the expected output. Okay. So the requirement is we need to implement the get and put operation with order of 1 time complexity. To achieve the lookup with order of 1 time complexity, we can use the map data structure. Okay. Map is an unordered data structure, but we need to order the elements in the cache based on their access time. The least recently used elements should be put at the beginning of the list. Most recently used will be put at the end of the list. Okay, so in order to maintain this ordering, we need to use the linked list. Okay, so whenever a new element comes in, we add it to the tail. Whenever a particular data is accessed, we have to put that as most recently used, so and move it to the tail of the list. Basically, we need to remove an element from the current location and put it at the tail whenever it is accessed. Okay, and also whenever there is a capacity reached in the cache, we have to evict the element present at the head. Basically, this involves node deletion in the linked list, but we want to achieve this in order of 1 time, so we can use a doubly linked list. With that, we can perform the deletion in order of 1 time complexity. Okay, so basically the LRU cache data structure will look like this. It contains a map, okay, and then it has a capacity and current number of elements in the cache, and then it has the head and tail of the linked list of all the key value pairs. Okay, so this map is used for quick lookup, and this linked list is used for ordering the elements based on their access time. Okay, let's quickly take a look at how the nodes in this linked lists are manipulated as we perform this operation. Okay. So first, after performing the first 3 put, the linked list will look like this. So first 1 is added, then 2, and then 3. So head is pointing to 1, tail is pointing to 3. Okay. Next, we are making a call to get with for the key value 2. So we are accessing 2. So once we access an element, it should be moved to the tail of the linked list because this is most recently accessed. So it will be put at the tail. So that's why 2 is moved to the tail of the linked list. Then we add the element 4. The linked list capacity is already reached. So we have to evict the element least recently used element, which is 1. So we have to delete this and then add 4. So that's why when we perform the put operation for the key 4, 1 is removed from the header linked list and then 4 is added. So 3, 2 and then 4. So the basic idea is whenever an element is accessed, that will be moved to the tail. Whenever a new element comes, the head will be removed and the new element will be added to the tail. That is what I have written here. Process the list of operations. If the current operation is init, we initialize the LRU cache with a given capacity. If the current operation is get, first we check whether the key exists in the cache map. If it exists, then mark that key as the current recently used and return the value of the key. Otherwise, we have to return -1. And for the if the current operation is put, then we check whether the key exists in the map cache map. If it exists, we update the new value for that key and then mark that key as the recently used. Otherwise, we check whether the capacity is reached. If the capacity is reached, remove the node at the head of the linked list and then create a node for the new data and add it to the tail of the linked list. Let's look at the flowchart. Input for the get method is LRU cache and the key value. Okay. First we check whether the key exists in the cache map. If it doesn't exist, we assign -1 as the return value and then return that value. If the key exists, then we assign the value of that key to the retval and then mark the key as the recently used. Basically, we move that corresponding node to the tail of the linked list and then return the return value. And next, let's see the flowchart for the put operation. First, the input for this procedure is LRU cache and then the key and the value. First, we check whether the key exists in the cache map. If it exists, then we update the value for that key in the cache map and then mark that key as the recently used one. Basically, move that key to the corresponding node to the tail of the linked list. If the key doesn't exist in the cache map, then we check whether the LRU cache capacity is reached. If it is reached, then we have to delete an entry for the key present in the head of the linked list. Okay, and then delete the node pointed by the head. Okay, then create a new node for the key value pair and add that new node to the linked list tail and then add an entry in the cache map and then increment the count. This procedure doesn't return any value. Let's move on to coding. First, I define the node structure, just key and value and then the previous and the next pointer. Next, I define the LRU cache data structure, which has cache map. It's a map of integer to pointer to a node, and then the capacity of the cache, and the count for the number of elements at any moment in the cache, and then the pointer to the head node in the linked list and the pointer to the tail. Then I implement the constructor function. I initialize the LRU cache structure with the empty map of int to pointer to a node, and then the given capacity. And then the count will be initialized to 0. Then head and tail will be set to null. Next I write the get method. First I check whether the cache map has an entry for the key. If the key exists, then I mark that key as the recently used. Then I return the value of that key. If the key doesn't exist, then I return -1. Next I write the put method. First I check whether the key exists in the cache map. If it exists, then I update the value of that key and then mark that key as recently used. If the key doesn't exist in the cache map, then I check whether the cache capacity is reached. If this is true, then I remove the entry for the key present in the head of the linked list and then delete the head node. So now we have a space for new node in the cache. Next I am allocating a new node for the incoming key value pair. Then I enqueue the node to the tail of the linked list. Then I increment the count. Then I add an entry in the cache map for the key. Next I am writing the mark recently used function. This function delete the current node and move it to the tail of the linked list. First I check whether the node to be moved is already at the tail. We can simply return. If it is not present at the tail, then we have to delete that node and add it to the tail. Next I write the enqueue function. So if the tail is null, then I set both head and tail to point to that current node. Otherwise, I add the current node after the tail. Next I write the dequeue function. First I remember the previous and the next pointer of the current node. If the previous node is not equal to null, then I update the previous node's next pointer to point to the current node's next pointer. Otherwise, the node to be deleted is at the head of the linked list, so I am just updating the head to point to the next. After updating the head, if that is null, then we have to update the tail also to null. Next, if the next pointer is not equal to null, then I update the next node's previous pointer to point to the previous pointer of the current node. Otherwise, the node being deleted is at the tail, so we have to update the tail. So the tail is now pointing to the previous pointer. And if the tail is null, then we have to update the head also to be null. Then add an entry in the cache map for the key value. Next I'm going to run the test cases. Compilation error. Let me fix those errors. I'm going to run the test cases again. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. We are given the list of operation and the corresponding input for those operation, and the expected output is null 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 1 null 3. Okay. The first operation is the LRU cache init operation with 2 as the capacity for the cache. Okay, so we initialize the LRU cache data structure with the empty map and the capacity and the current number of elements in the cache and the head of the linked list and the tail of the linked list. Okay, so first the cache map initialized with empty cache map and the capacity is set with 2. The count is initialized to 0 and head and tail are pointing to null. Okay, next we have put operation. So here first we check whether the element is present in the cache. In this case it is not present. Then we check whether the capacity is reached. That is also not true. So we allocate a new node for that key value pair 1 comma 1 and add it to the cache map, and then we enqueue that to the linked list. So it has only one node, so both head and tail are pointing to 1. Next we have a put operation 2 with key value pair 2 comma 2. So in this case again we check whether there is an entry exists for the key 2. In this case it is not. So we go ahead and check whether the capacity is reached. The capacity is not yet reached because the count is 1. So we go ahead and allocate a new node for that key value pair 2 comma 2 and then add an entry in the cache map. So we have 2 entries now, and then we add the new node to the queue and increment the count. So now the linked list has 2 nodes and the head and tail point to 1 and 2 respectively. Next operation is get. Okay, so the get operation, we check whether the key exists in the cache map. It does exist. Then we mark that node as recently used, meaning we have to move 1 to the tail of the linked list. So that's what we are seeing here. So that 1 is moved to the end of the linked list. Okay, so the always the head is the least recently used and the tail points to the most recently used element in the cache. Okay, and then we finally return the value of that entry, which is 1. Next we put the value 3 comma 3 into the cache. We check whether there is an entry for the key 3. It is not. So we go ahead and check whether the capacity is reached. In this case the capacity is already reached, so we have to evict the key present in the head of the linked list. So the head of the linked list is 2. So we have to evict 2 out of this cache and then we dequeue that head. Okay, and then we allocate a new node for the value 3 comma 3 and add it to the tail. So now after removing 2 and then adding 3 to the tail, we have the new linked list 1 and 3 in the linked list. So next we do perform the get operation for value 1. So we check whether the key 1 is exists in the cache map. It is present. So we go ahead and mark that node as recently used by moving node 1 to the tail of the linked list. Okay, and then we return the value 1. Next I'm going to do the time and space complexity analysis for this solution. The time complexity for this get and put methods are order of 1. Okay, if you look at the get method, we are doing the lookup in the map data structure, so which takes constant time to look up any key value, and then we do call the mark recently used function. Okay, so if you see this function dequeue the element from its current position and then move it to the tail of the linked list. Okay, so if you look at the enqueue and dequeue function, they are all done in constant time. Basically we are using the head and tail pointer. We always use the tail pointer to add an element to the queue. So this is done in a constant time. And if you look at the dequeue, this is also done in constant time. We are not traversing the linked list to locate an element. Instead we directly get the previous and the next and do the link manipulation in constant time. Okay. Similarly for the put operation, look up the map data structure, which it is done in constant time, and then it calls the mark recently used, and then dequeue function and enqueue functions all are done in constant time complexity. Okay, so that's why the time complexity is order of 1 for these two methods. Space complexity is order of n, whereas n is the capacity of the cache. Okay, so if the capacity is 2, at most cache will need to have space for 2 elements. So the space complexity is order of n. Thanks for watching this video. Have a great day.